Hello guys. Today we have a list of the top 6 Andrew Tate. Número 6. Andrew Tate Software.
Finally, someone let me out of my.
I'm ugly and I'm proud.
Yo, who the?
Rate 5 please.
What is that?
Hey everyone, I am James Senior. I'm Voltes Benny. I am James Francis Dominguez. I'm Joseph Connor. I am and we are the Robo, your reporters for today's video.
So our topic for today's video is manner of polymerization. So a polymer is a substance that is made of very large molecules that are in turn made up many repeating units called monomers. Polymerization is the process through these monomers come together to form the macromolecules that constitute polymers. Polymerization is a chemical process divided into two broad categories such as condensation polymerization and addition polymerization. In addition polymerization, similar monomer unit continuously add to the active site such as double band or triple band. This product is a homopolymer. Polymerization reaction is initiated by organometallic compounds or organic peroxide. Polyethylene or polyethene is a product or addition polymerization of thousands of ethene, whereas ethene molecules. Here are some examples. Moving on, let's continue with condensation polymerization. There is a loss of small molecules like HOH, HCI, or NH3 between two usually different molecules. This ensures continuous polymerization into heteropolymer or copolymer. The condensation reaction between hexamethylene or diamine, whereas 1,6-diaminohexane, and adipic acid, whereas a dicarboxylic acid, produces nylon 66. A water molecule is lost in the process. Here are some examples. Hexamethylene diamine, whereas 1,6-diaminohexane, and adipic acid, whereas a dicarboxylic acid. When you combine them, they will produce nylon 66. And that is with my part. I will now pass the floor to Von Casmiranito.
Thank you, Mr. Polieros. Now let's move on to the next topic, the mechanism of polymerization. Now, addition polymerization reactions are usually catalyzed by peroxides. The energy is provided by heat and sunlight. Now, these peroxide catalyzed reactions generally occur under the free radical polymerization. But first, what are free radicals? Well, free radicals are highly reactive chemical species that contains an odd or unpaired electron. Now, back to addition polymerization. Polymerization reactions occur in 3 stages: initiation, propagation, and termination. In the initiation stage, the peroxide radicals, for example, a hydrogen peroxide, would break apart into 2 free radicals. Those free radicals would then find a monomer and destroy its double bond. This would form an activated monomer, which is itself a free radical. Now, since a monomer has been activated, the propagation stage begins. The activated monomer would find another monomer and would destroy its double bond. If this can be repeated many times, this would form a polymer chain. Now, the length of the chain would depend on the reaction conditions. And finally, the termination stage begins when the polymer chain attaches to a free radical. These could be the original free radicals, the polymer chain, or even one of each. Coupling, chain transfer, and the inhibitors written in this chart was not mentioned in the module. As such, I will not mention any of those. It may be tackled in the next topic. Now, condensation polymerization occurs through an entirely different mechanism. In condensation polymerizations, the monomers usually have two reactive sites of functional groups, such as alcohol, amine, and carboxylic acid groups. The reactions occur through an ionic mechanism that depends on the nature of these functional groups. Now, some monomers can have more than two functional groups. These allows for branching between chains and increasing the molar masses of the polymer. And that's about it, the mechanism of polymerization, all you need to know. Now, Mr. Mingus will take the stage about the tacticity of polypropylene.
Thank you so much, Inito, for that wonderful presentation. So for our next topic for today is toxicity of polypropylene. So to start us off, stereochemistry deals with the study of the spatial distribution of atoms in a compound and its effects on the properties of the compounds. Because of the nature of covalent bonds, different groups in a given molecule can have different orientations in space. Here we have our first polymer that we are going to talk about, polyethylene. Here we can see its structure. It is composed of 2 carbons, 4 hydrogens, and it is composed of different chain lengths, tangled crystalline regions alternate with amorphous regions with metal branch at about every 10th unit. Here we can see its properties: waxy, dissolved fats, oils, grease slowly, translucent when pure, resistant to moisture and chemicals, excellent electrical insulating properties. Here we can see its uses. For HDPE, its bottles and caps for milk, soft drinks, liquid soap, pipes, and tubings, molded objects like crates, electricable jackets. For LDPE, we have packaging films and sheets for food and garments, tubings, squeeze bottles. For the second polymer that we are going to talk about, here we have polyvinyl chloride, or otherwise known as carcinogenic gas. It is composed of 2 hydrogen, 3 hydrogen, and 1 chlorine atom. It is linear. It does not pack well because of the large chlorine atoms. Its properties are: it is versatile, can be mixed with a wide range of additives, non-permeable to alcohol and oily products. It is rigid, strong, high density, low softening point, chemically resistant. Its uses are for toys, raincoats, shower curtains, phonograph records, plumbing pipes, credit cards, garden hose, rigid clear bottles, vinyl sheets, surgeon's gloves, and building products. Here we have our third polymer that we are going to talk about, which is polyacrylonitrile. It is composed of 2 carbons, 3 hydrogen, and 1 cyano group. Its properties are: it is resistant to microorganism attack, and it is degraded by sunlight. Its uses are for fibers, Orlon, acrylon, copolymer with vinyl acetate, copolymers used for carpets and wigs. Here we have our fourth, second to last polymer that we're going to talk about, phenyl formaldehyde, or otherwise known as bakelite. Here we can see its structure. It is hard or rigid, black, and good insulator. Its uses are for molded objects like telephones and household appliances, insulation for power plugs, points, and switches, and for electric jug lids, varnishes, and lacquers. Here we have our last polymer that we are going to talk about, which is polyethylene terephthalate. Here we can see its structure. It is stiff, grease resistant, very strong, high electrical resistant, orderly arrangement of molecules. Its uses are for textiles, mylar films, and for cassette tapes, balloons, artificial blood vessels, replacement skin for burn victims, feeding bottles, adhesive pistol grips, explosion barriers for TV tubes, bowling balls, paint, enamels, and false teeth. Applied to polymers, toxicity is a special term that refers to the way the pendant hanging groups are arranged on the polymer backbone. Polypropene or polypropylene exhibits three kinds of structures which differ in the spatial orientations of branch groups. It is isotactic when all metal groups are on the same side and syndiotactic when these groups are at alternate positions. When the metal groups are randomly arranged, the structure is called atactic. That structure can be pre-planned by the selection of the proper catalyst during polymerization. Figure 2 illustrates the structural formulas of the different stereoisomers of polypropene. Atactic polypropene has little order in the polymer backbone. This makes it amorphous. The common name for amorphous polypropene is linear low-density polypropene, or LLDPE. This polymer is clear and used in soda bottles. Atactic arrangement of branches causes loose packaging of polymer chains. This polymer is less dense and less tough, but more flexible. Isotactic and syndiotactic polymers have ordered structures and therefore have higher crystallinity in the polymer chain. The longer range in order in isotactic polypropene adds mechanical strength and crystallinity. HDPE is used in laundry detergent bottle. It is not translucent like LLDPE. The terms for three orientations come from the Greek word taktos, ordered, which is modified by the prefixes iso, same, syndio, meaning together, and nine, not. In 1953, Ziegler and Giulio Natta, Italian-born, 1903, professor of industrial chemistry at Milan Polytechnic, independently prepared the highly ordered polypropylenes, thereby creating the first stereochemically ordered polymers. For their pioneering work, Ziegler and Natta shared the 1963 Nobel Prize in Chemistry. As we expect from our knowledge of the effects of molecular order on the melting points of triglycerides and on the hardness of polyethylenes, the highly ordered isotactic and syndiotactic polypropylenes are higher melting, more crystalline, and harder than the atactic. And that's it for today. Thank you for listening. I hope you learned something new. I will now pass the floor on to John Sibes Morelio and Eldridge Mozo.
Thank you for that long and exquisite report, Mr. Mingix.
Yes, now we're going to talk about the structures and properties of polymers.
Hydrocarbon polymer structures and properties are linked. Polymer chain's physical characteristics are influenced by its average chain length, degree of branching, and type of component monomers.
Yes. Thermoplastic linear polymers include those made from aliphatic hydrocarbons. Chains that are highly linear and have fewer branches can pack tightly. They produce high melting point and high density polymers.
High-density polyethylene or HDPE may contain between 10,000 or 100,000 carbon atoms, while low-density polyethylene has shorter branches and may contain as many as ethylene units. Increasing branch chains or molar mass may improve mechanical properties such as strength, toughness, and chemical resistance.
That's right. LDPE is more flexible, more extensible, and tough than HDPE. HDPE has a greater melting point, more powerful, more stiff, but less robust, less extensible, and more opaque. Better mechanical characteristics are obtained when the polymer molecules' mass lie within a small range as they opposed to when they are dispersed across a large range.
Polymers with more branch chains are more flexible and has lower densities. Hydrocarbon branch polymers are more susceptible to oxidation.
That's right. Cross-linking weakens and increases the polymer's brittleness. Most durable and thermosetting are cross-linked polymers.
And that's all about the structures and properties of polymers.
We have Ian for the silicates polymers of the lithosphere.
Thank you so much, Mozo and Sibes, for that goofy report. Now, let's move forward to the next topic, which is silicates polymers of the lithosphere. But before I start, I have a short trivia. Do you know that not all polymers are organic compounds? Some polymers are inorganic, like polyethylene, polypropylene, and silicone, which I am going to discuss. Let's go. The most abundant inorganic polymers are compounds of silicon and oxygen. The clays, rocks, and inorganic soils makes the Earth's crust are primarily composed of silicon and oxygen. The planet's crust, which is made up of the outermost layer of land and water, is typically 46% of oxygen and 28% of silicon in mass. The majority of the Earth's crust is made up of polymers containing silicon dioxide, SiO2, containing silicon dioxide with repeating units, and ionic aggregates like SiO3, trioxidosilicate, SiO4, orthosilicate, S2O5 kaolinite, S4O11, and so forth. In these, 4 oxygen surrounds each tetracovalent silicon, in much the same way as 4 hydrogens occupy the tetrahedral methane molecule. But while methane's hydrogen are monovalent, monovalent means having 1 valence, the oxygen's atom is divalent. Divalent means having valence of 2. So they either carry negative ionic charge or bond to a silicon atom. With the other elements of crust, such as aluminum and iron, these inorganic polymers form much of the substances of the Earth's rocks and minerals. So, what is asbestos? Asbestos, dili ni siya scientist. Guys, dili ni siya scientist. Asbestos is a natural carcinogen that causes mesothelioma. Gamiton ang asbestos, guys, sa brake linings o cigarette filter and insulation sa mga balay, buildings o sa eskwelahan. With the other elements of crust, such as aluminum and iron, these inorganic polymers form much of the substance of the Earth's rocks and minerals. Let's move forward. So, unsa din ang mesothelioma? Mesothelioma is a cancer of the lungs and the cavity of the chest and the abdomen. So, what year nag-start ang asbestos? Asbestos started since the mid-1970s. The mineral has been abandoned as insulating material in the construction. So guys, short rasad nga paibalo, ang symptoms sa mesothelioma kay chest pain, shortness of breath, fatigue, a high temperature and sweating, particularly at night, a persistent cough, loss of appetite, and unexplained weight loss and club fingertips. In the quartz lattice, every oxygen is shared by 2 different silicon atoms, one at the center of each 2 adjacent tetrahedral that are connected through the oxygen. Each silicon atoms own, in effect, exactly half each of the 4 oxygens bonded to it, with the other half assigned to this other silicon atom to the oxygen. 3-dimensional lattice of silicon, SiO2. And that is with my part. I hope inyong memorize ang katong akong short nga paibalo. So I will now pass the floor to Hope Wesley Segundo.
So our topic for today is silicones. Now don't be confused with silicon and silicone. As Ian mentioned earlier, silicon is a natural chemical element, while silicone is a man-made polymer. An organic Si group chain forms the backbone structure of silicones. This one right here is an example of an silicone. An organic group is bonded to Si. This one is an organic group. This one also is an organic group. Now, silicones are typically linear. That means they only have one backbone. Side group can be introduced to form crosslinks between chains. This one right here, this is a crosslink silicone. And the general formula for silicone is R2SiO2. Silicones are chemically inert, heat-resistant, rubber-like, and have low toxicity. These properties make silicone suitable for a wide variety of applications. These include many industrial applications as well as medical uses. That's all for Group 2. Thank you for listening. Okay, cut.
Ah!